talking to the speaker in the morning, and what I gathered is that there was some repetition. So I hope that because of the repetition, you get to understand some of the things. So you guys talking about total factor productivity, panel data, and some also applications of stochastic frontiers. Now the slides that I have in here, this is related to what we call multiple output or multi-product technology. Now these slides are somewhat advanced, so what I'm going to be doing is, as before, I'm going to be starting with something simple and then try to get to some of the slides, not all. Okay. So what is the idea of multiple technology? Now remember, I was talking about production processes with only one output. Okay, so we were saying y is a function of some input variable. And I was giving you examples like if you look at farmers, they're producing wheat and they're using land, labor, capital, fertilizer, and things like that. Okay. Now you might just say, well, the farmer is again not only producing like a wheat, but also producing tomatoes, potatoes, and things like that. I mean, in different lots. So the problem is that if you ask the farmer, do you know how much fertilizer you are using for the tomatoes, how much for potatoes, how much for wheat, and how many people are working on each of those things? Usually, we don't have the breakdown. So he can tell you that, well, okay, for fertilizer, my total expenditure was like, for example, 5,000 rupees. For labor, it's 10,000 rupees and things like that. So what you have is, you have data on the production of various outputs, okay? But so far as the inputs are concerned, you don't have the input allocation for each and every output. So then again, what you can think that you have the input variables, okay, and then output variables, but input variables are not cancel. So the input variables are not specified for each output. So what we'll be doing is to relate it to the production function that I introduced from the beginning. Let's just start with something slightly different, and then again we just get to the production function. So instead of one output, since we are going to be talking about multiple output, we start with the technology that we can write mathematically in this form. Okay, let's just get to the back one. So you have f of y, x, okay, and then again if you want, you can put some other variables, but let's say that one, we just close it in here. So y is a vector, meaning that you have more than one output, and again x is also a vector, meaning that you have more than one input. Okay. So what happens if y is a scalar? Then from this production function, you can write simply y is something like this. Okay. Now, but if you have multiple outputs, then you cannot do something like that. So we don't call this a production function, we call this a transformation function. Just a different name. So what this transformation function is doing is, you can think in terms of a process in which the inputs are being used in one end and outputs are coming on the other end. So that type of thing. But the difference is that you have more than one output. Okay. Okay. So this is kind of the setup. So to start with, I am not assuming any inefficiency. So again, this is a transformation function with more than one output. So again, as I said, what you can think in terms of y is y1, it can be wheat, and then you have another output y2, it can be tomatoes, or again many other things, but again two outputs is enough to describe the situation. Okay. So I mean you can spare, you can make some simplification for f. So again you can think in terms of f of y2, yx. Okay. So this you can write it out like this, that for example f1y times f2x is equal to a. So again we are assuming this is output and inputs are separable. So f1 is the output function, and then f2 is the input function. And if this is the case, it will be clear that if your y is a scalar, then again you can just write this as y equal to f2x times a or something like that. Okay. Okay. So you can see the relationship going from one output to more than one output. Okay. So now what we need to do is we need to specify some functions. Okay. So we talked about Cobb-Douglas. So you can think in terms of both f1 and f2 are Cobb-Douglas. Okay, so this is just kind of an example. Okay, so if that is the case, remember the way we write Cobb-Douglas. Again, this is just a productive, product of all the inputs and product of all the outputs. So you can just write f1 like this. You can write y1 to the power alpha 1, y2 to the power alpha 2. So this is for f1. And for f2, since this is x, you can write x1 raised to the power beta 1 and x2 raised to the power beta 2 and so on. You can have more than 2 inputs, right? Okay, so what happens is that if you write it in terms of log, then again it's going to be linear. Okay, so if you take a log, so log of f1 plus log of f2 is equal to log of a. And log of a you can think in terms of being equal to constant plus the term b, that is embedded inside a. Okay, so you can think in terms of writing it out like this. So that means if I write it out fully using this f1 and f2 that I have in there, I can get alpha 1 y1, sorry, log of y1 plus alpha 2 log of y2, and then again, so this is the output function part, and then again like beta 1 log of x1 plus beta 2 log of x2 and so on, and then on the right hand side you will be getting beta 0 plus b. Okay. Now when you write it out, it's clear that again you cannot identify all the parameters. So you need to, let me just do it like this, cannot and remember when we were talking about single output production function, we were writing y1 on the left hand side and then x's were on the right hand side. So what was the coefficient on y1? There was no coefficient, right? So we were assuming that the coefficient of y1, or you can just say that alpha 1 is equal to 1. Okay, so this is the reason I just said, well, we cannot identify all the parameters, So then again, we need to normalize. So in this setup, you need to normalize one coefficient, okay, to be equal to 1 or something of that sort. That means you cannot identify all the parameters, right? So some sort of a normalization is necessary, okay. So let's just look at this way. So if you normalize alpha 1 to be equal to -1, okay, or 1, doesn't matter which way you go. So if you do this, then what is happening is minus log of y1 plus alpha 2 log of y2 plus beta 1 log of x1 plus beta 2 log of x2, and again other is equal to beta 0 plus b. So what you can do is you can take y1 on one side and then the rest of it is on the other side. So if you do that, then you can write log of y1 is equal to, okay, so this looks like a production function, or maybe just write it out like this, alpha 2 log of y2, because I'm taking this guy on the other side, plus beta 1 log of x1 minus plus beta 2 log of x2, and then again I'm bringing this to this side. So minus beta 0 is equal to, not equal to, that is equal to. So I'm taking this on the other side. So this is minus beta 0 or minus b. Okay. So this looks like a production function. Right? The reason I'm just saying it looks like a production function, you are just saying that, okay, you have one of the y on the left hand side and you use the other y on the right hand side. Now the question is, there is a problem in here. So which y is to be used as the dependent variable? Okay, so if I give you the data and I don't specify which variable is, for example, wheat, which variable is potato, which variable is tomatoes, and then again, I just have a y1, y2, y3 instead of specifying. When I'm asking you to, do the estimation. So the first question would be, which one do you want to put as the dependent variable, like that on the left hand side. So if I give this as an assignment, some people might be using wheat on the left hand side, some might be using potatoes, some might be using tomatoes. So there is no, when I assign it, there is no guarantee who is going to be using which variable on the left hand side. Okay, and because of that, results are going to be all over. Okay, the results are going to be very different. There is one group who is going to be using this formulation. They will have one sort of result, and then the other group who is going to be using a log of y2 on the left hand side, they will be getting a different type of result, right? So although it looks like a production function, this is a problem. And then the other problem is that this is econometric. So this y2 is going to be correlated with the random term p. So like your estimation that we are talking about, will give you inconsistent estimates. Your estimates won't be unbiased. So this is not a valid procedure. That means even though you can get from here to something that looks like a production function, that idea is problematic. So we always say that, well, if you are dealing with multiple output, you do not do or do not estimate the relationship like this. Okay. So then what we do is, you can think in terms of using a different type of normalization. So let's just look at the second type of normalization. So let's just look at this, alpha 1 plus alpha 2 is equal to 1. So remember, you have to get rid of one, there is one extra parameter. You have to get rid of that. So 1 is just we use normalize them to be equal to 1, and this is the second way of doing it. I'm just saying that well, sum of the alpha is equal to 1. Okay. So if sum of the alpha is equal to 1, you get to estimate only one alpha. The other alpha would be coming from the relationship that alpha 1 plus alpha 2 is equal to 1. Okay. So let's just work it out. If alpha 1 plus alpha 2 is equal to 1, then you can just go back to this function in here, okay, and write it out differently. Okay. So let me just go back to this part in here. Okay. The part I have in there, and let me just get it in here. Okay. Okay, so this was the equation that I started with, right? And then again I'm just saying that well I'm going to be using alpha 1 plus alpha 2 is equal to 1 as my normalization. Okay. So then again you can think in terms of alpha 1 is equal to, this means again you can just say alpha 1 is equal to 1 minus alpha 2 or that type of thing, right? So now again let's just replace alpha 1 by 1 minus alpha 2. So I can write 1 minus alpha 2 and then log of y1 plus alpha 2 log of y2 plus, I'm not writing all this thing because these are identical, right, as before. I'm playing with the first part, okay. Now again like this means, again take the bracket out, so get log of y1 minus alpha 2 log of y1 plus alpha 2 log of y2, right, plus things. This is simple math, I'm just going step by step, okay. So that means log of y1, and then if you look at these two together, you have alpha 2, you have alpha 2, so alpha 2 is common, right. So you can just write plus alpha 2, okay. Now something is alpha 1 is equal to 1 minus alpha 2. Okay, this is log of y1. Okay, so you have alpha 2, so I can take alpha 2 common, and then I'm getting it log of y2 minus log of y1, and then the right hand side is exact, I mean the rest of the term is fine. So now the last line, I have log of y1 plus alpha 2, and then I can write this as log of y2 over y1. Right? So then again, finally I can write log of y1 and then throw everything on the right hand side. So that means you can do it like this, minus alpha 2, I'm just taking everything to the right hand side, log of y2 over y1, and then the other terms which are going to be equal to beta 1 log of x1 minus beta 2 log of x2, things like that. So what is the difference? This is the final. So what is the difference? The difference is that while in the previous specification I had log of y1 on the left hand side, and then again log of y2 was on the right hand side. Okay. So now if you look at it carefully, you see the right hand side variable in y is in the ratio 4. Okay. So that is the key. So this is called output distance function, and the reason is that it does not matter which y you put on the left hand side. Instead of y1, if you put y2 on the left hand side, this is going to be y1 over y2. So the right hand side variable in output has to be expressed in the ratio 4. And you see that nothing is happening to the x variable. That means the coefficient of x variables are going to be exactly the same as before. So this is called an output distance function.
This meeting is being recorded.
Or or in short, this is, we call it ODF, okay? So again, in essence, what is the output distance function? Okay. So output distance function means that you have one output on the left-hand side, the other outputs are going to be on the right-hand side, written as a ratio of the output quantities, okay? Nothing happens to the inputs. We were talking about y on the right hand side correlated with the beta, but now it's in the ratio. So both y2 and y1 are going to be related to v exactly the same way. So when you take the ratio, they will cancel. Okay. So you don't have the calorimetric endogeneity problem. Okay. So this is a popular approach that people use when it comes to estimating multiple output relationship. Okay. Okay. So again, as I said, well, if you want to do it with your, and again, this is going to be related to output-oriented inefficiency that I'll be talking about in a minute after I finish this. Okay. So again, this looks like again not exactly like a production function. The only difference is that the right-hand part of the y variables are to be in the ratio form. And again, if you just evaluate which ratio, well, that depends on what you put on the left-hand side. If you put y3 on this side, this is going to be y1 over y3, and then y2 over y3. Right? So all the outputs are going to be expressed in the form of a ratio. Nothing happens to the inputs. Okay. So that's kind of the output distance function. And again, you can do it with or without inefficiency. Right now, I'm talking about a specification without inefficiency. Okay. So now let's just do a different type of normalization. Okay. So we go back to the same function that I was dealing with. Okay. So now I'll be doing this third thing. Okay. So use normalization. Now I'm going to be playing with betas. Right? So think of only two x's, and I'm doing this normalization beta 1 plus beta 2 equal to 1. So remember I told you that there is one extra parameter and you have to get rid of that in some way. So right now I'm just saying that, okay, let's assume sum of the betas or sum of the input elasticities is equal to 1. Okay. If you have 2, that's fine. If you have 3, no problem. Any number of x can be there. All you do is like this. Sum of beta j equal to 1 if there are more than 2. Okay. So then again you do the same manipulation that I was doing. So that if this is the case, you can write beta 1 as equal to 1 minus beta 2, and then again replace beta 1 in here by 1 minus beta 2, and then again just go through the lines that I was doing. And if you do that, then you will be getting an expression that will look like this. Log of x1 is equal to, on the right hand side, you will be getting minus beta 2 log of x2 over x1. Okay, and then again you will have the output quantities, which are outputs are like alpha 1 log of y1 minus alpha 2 log of y2 and things like that. Okay, so what is happening? If you are careful, you will immediately see that, well, what I have done is nothing but switched x with y, right? If you switch x with y, then what I have done and what I got, how I got the output distance function is going to be exactly the same as, again, this is input distance function. That means simply, if you do the math, then you will say that, okay, after doing the first one, you don't need to do the second one. Like if you are taking a test, you might just say that, well, okay, go to the previous derivation and replace x with y, and then again you are done. Okay, so this is called input distance function. Again, this is just a name. And again, this input distance function has similar properties. It doesn't matter which x you put on the left hand side. The only thing is that well, the right hand side x variable are to be expressed in the ratio form. Okay, and then again, nothing is going to happen to y. Okay, so those parameters are going to be unchanged. We have a minus sign because of the fact that I use normalization beta 1 plus beta 2 equal to 1. If I say beta 1 plus beta 2 equal to minus 1, then you don't have the minus sign. But again, like minus or plus, what I'm talking about is the absolute value of those alpha 1, alpha 2. Now you get beta 2, you are not getting beta 1. How do you get beta 1? Once you get beta 2, you can get beta 1 by looking at this relationship. Right? So you are basically getting all the parameters. Okay. Okay, so the last one is, again, or maybe I should have done it in the third place. So the fourth one is, again, similar to the production function. So let's say our normalized beta 1 is equal to 1. Instead of beta 1 plus beta 2 is equal to 1. Okay. You just use beta 1 equal to 1 as your normalization, and you go back to the function that you see here. Right. So you put beta 1 is equal to 1, and then again, so that means there is no coefficient in front of x1, so then you can write log of x1 equal to, so this is one, and again throw the other numbers on the right hand side. So you will be getting, let's just say minus beta 2 log of x2 minus alpha 1 log of y1 minus alpha 2 log of y2 and so on. So this is again sometimes called input requirement function. So this simply says that if x1 is labeled, for example, then this tells you that what is the minimum number of people that you need to produce a given level of y1 and y2, and given the quantity of land and labor and land and fertilizer and things like that. So you are picking up one input out, and you just say that well, your focus is on the labor use. And you just say, well, what is the minimum number of labor that I need to use, given the quantity of land, fertilizer, and other things, to produce a bundle of wheat and corn and that type of thing. Okay, so this is similar to production function. Remember again, if you are observant, you will immediately say that well, 1 and 4 are exactly the same when you replace x with y. Because in 1 we had a log of y1 on the right hand side, left hand side. Now I have log of x1 on the left hand side. So if your x and y are flipped, then you are going to be getting exactly this expression. So this is again in a sense mirror image of this production function. Now again in practice, 1 and 4 are not used much, because of the fact that you have the same situation. You might motivate in your research that well, my objective is to figure out what is the minimum amount of labor to use. But then other inputs, again your x2, x3 and x2, x3 might be also variable input. You might be thinking in terms of minimizing your cost. Remember when we were talking about cost minimization, we just said that your objective is to use the inputs in a way that your cost is minimized. Okay, so you are not choosing one axis. You are choosing all the inputs in a way so that your cost is minimized. Now here again you are looking at x1 on the left hand side. If I give this project to people in the class, some might be using log of x1 on the left hand side, some other might be using log of x2 on the left hand side. So again, just like the production function that I was talking about, your results are not going to be invariant. Okay, so the question is that who is right? Well, nobody is right, again, because everybody has problems. Okay, and the problem is, again, you are just looking at one x, and then this x is going to be correlated with the error term. So you have econometric inversion. Okay, so this is, again, you can think in terms of the ones that I talked about is basically output side and the input side. So the normalization is based on in terms of the inputs or the outputs. Now you might be saying that, okay, since I am free to choose any kind of normalization, how about taking one of the alphas and one of the betas and just say that, well, alpha 1 plus beta 1 is equal to 1. You can do that and you will be getting some expression, but that expression has no meaning, or it will be again subject to similar type of problems that we have in 1 and 4. So in the literature, what we use most of the time, again, this is kind of the state of the art in the sense that, again, if you are dealing with multiple outputs, then you have to use either input distance function or output distance function. That means number 2 or R3. Okay. Now the choice is that, well, what do you want to use? So let's say that, well, you are looking at banks. So for banks or any other services, if you go into the hospitals produce many different types of output, right? And outputs are the different types of, let's say, the surgeries and other things that they do. So there are many different outputs, and then the question is that those outputs are given. So in that case, your objective is to minimize cost. So you have to serve the patients in a way that your cost is minimized. So in that case, you should be using input distance function. Okay. On the other hand, if your objective is to maximize revenue and your input quantities are given, then you should be using output distance function. So there are some clear cases where to use input distance function or output distance function. But the main point is, again, you have to use one of the x's or one of the y on the left hand side, and the variables on the right hand side have to be expressed in the ratio form. Okay. Any question? Okay. So you shall see that, well, this is kind of a very important area of research because we do not deal with, although we spend most of our time in talking about single output, but in practice, most of the production processes are multiple. Now we might just say, well, what would be wrong? Because I started by saying that, okay, you look at the data, and the data say that different types of output that the farmer is producing, okay? Or if you are looking at banks are not producing one output, they are also producing different types of output. Hospitals, there are different types of output. So again, the question is, can you do one at a time? If somebody says that, okay, can I do something like this? I look at wheat, and can I estimate a production function using wheat and all the input quantities? No, that would be wrong because you are looking at wheat, but look at the inputs. The inputs are not specifically used for the production of wheat. The inputs are used for the production of tomatoes and potatoes also, because I don't know the exact amount of these inputs that go to different type of outputs. If I know, then again there is no need to do multiple output production function. You can just do a single output production function. Okay, so that's basically what the tools are when it comes to multiple inputs and multiple outputs. And again, I just did it without inefficiency. So now we can bring inefficiency into the picture, and things would be quite similar. So let's just say, well, we'll bring inefficiency into the picture. Maybe I have a lot of stress. So now introduce inefficiency. Now again, the question is, again, what type of inefficiency you want to use? Is it output oriented or input oriented? Okay. So let's just say, well, if you are using output oriented inefficiency, remember that is associated with output, right? And input oriented inefficiency is associated with inputs, right? So when you transformation function, which I wrote like this, y1, y and x is equal to a. So now I have to write it like f of y times e to the power u, and then x is equal to a. So this is U is your output oriented inefficiency. Okay. So what is happening is your actual output is Y, okay, but you are inefficient. So your potential output is Y times e to the power U. That means you can produce more than what you are actually producing. Okay. So then again what you do is, okay, in this case, instead of going through all the algebra, meaning all over again, let me just say that, okay. So if this is the case, and again you use a simplification that is your F1, okay, you just say, well, these are separable. I mean, this is an assumption. If you ever look at the notes that I have in here, I do not assume separability, okay, but again that involves again a lot of algebra, but the point is that, well, the separability is not a requirement. So if it is separable, then you can just write F1, Y, and then e to the power U, and then again times F2, and then again this function of x is equal to a, something like this. So your inefficiency part is associated with the output function, and then input function is not related to that because I am using output oriented. Okay, so let me just erase this part because I'm just using output oriented inefficiency, and then again I'll get to the input oriented part once I finish this. So now going back and just say, well, what is new in here? Your y is replaced by y times e to the power u. So y is a vector, but u is so e to the power u is a scalar. That means, again, this is an assumption. That means you are talking about many different outputs, but their inefficiency, meaning that because of inefficiency, all the outputs are proportionally produced less than what you could produce. Okay. So again, like this is kind of an assumption. So this e to the power u is a scalar, but y is a vector. So you go through the same type of algebra. So if we assume a Douglas functions for both f1 and f2, then again, like I'm not going through all of it. So you'll be able to say that log of y1 is equal to, on the right hand side, you'll be getting now let's look at this log of y2 over y1. Do you think that there will be, inefficiency is going to be affecting the ratio? If each and every output is reduced by 10%, what will happen to the ratio? Ratio remains the same. So again, although I'm replacing y by y times e to the power u, the ratio is not affected by this. And this one is going to be like this. Because again, I just said, well, all you do is be observant, and then you just see that instead of mechanically doing it all over again, you just say, well, do I want to repeat it? The answer is no. Whenever you see y before, now you replace y by y times e to the power u. Right? Now in here, e to the power u is redundant because again they will be cancelled, but e to the power u is appearing in here. And then again you will have minus or plus, whatever I had, I think I had all minus, beta 1 log of x1 minus beta 2 log of x2 and things like that. Okay. And then again plus or minus v, so let's just put v in there, and again plus or minus doesn't matter, but again if you want to derive it, be consistent, don't change the sign. Okay. So now again what you do is you can just say that, well, this means log of y1 is equal to, you have everything in there, and then again take u to the right hand side because log of e to the power u is u, so then again you are getting v minus u. Okay. I want to focus on that part because this is something new, right? And you would like to know whether you need to use a different software or different estimation method. So look, at the right hand side variables, okay, are different now. Before, when I was talking about a production function, I had it only x, right? But in addition to x's, I have the ratio of outputs, okay? But again, think of this as an additional variable. Okay, so when you run a regression, remember in simple regression, all you do is that while you click on variables that you want to use. You might have 10 variables, sometimes you might have 12 or 15, it doesn't matter. The regression is you just click the variables that you want to use as independent variable. So the independent variables now are not only just the x's but also the ratio of y's. Now if there is no y2, so then again this time will drop and you will be getting back to the standard production function that we have been talking about for some time, right? So now again, when you look at this, again, this error term is the same error term that we started talking about from day one, right? This is a noise and inefficiency. So then again, do you need anything else? That means the static code that was used before, right, for half normal or truncated normal, you use the same static code, right? Because this is v minus u, right? Okay. So then again, what is happening is that this is the only additional term that you need to use. So this is the only additional term that you have to use. Okay. If it was a single output, you will have simply the x's on the right hand side, and since it is a multiple output, you have to use the ratios of output. If you have 3 outputs, then you add another term that would be y3 over y1 and log. Okay, and so on. So the number of again outputs does not change anything so far as estimation goes. Okay, and then again, so again, as I said, well, the estimation is not an issue, and the interpretation of inefficiency. What was the interpretation before? We were talking about output shortfall. Again, here you have also output shortfall, but again, that shortfall is not for only one output, but all the outputs. The problem here is that, okay, you have to make the assumption that the shortfall of all the outputs are exactly the same. Okay, I mean, you would like to say that, well, I mean, the model is general enough to allow the possibility of different amount of output shortfall for different outputs, but we have not been able to figure out this different EU for different Y. Okay. Okay, so this is basically again output distance function with inefficiency. So again, I'm just repeating that what stochastic frontier codes that you have seen are the same codes can be used, except for the fact that you need to add these terms. Okay. Now again, okay, if you look at the output input distance function with inefficiency. Now I'm lazy, I'm leaning on this thing, that's why my lines are not straight. Okay. So again, so inefficiency is in the inputs, right, this time. So going back to this, and then if you start with F1 and then Y, and then times F2 times X, but now I have to do something like this. Right? Because your X is the amount of X you are using, but you should be able to use less than that if you are efficient. Right? So now this is again like a input-oriented inefficiency. And on the right hand side you have A. Okay. So then again, like you go through the same lines of algebra, and then you will be saying that, okay, log of x1, okay, on the right hand side you will be having beta 2 or minus beta 2 log of x2 over x1. Now let me just change this to this, because x's are replaced by x times e to the power minus eta. What will happen to the ratio? If all the x's are changed proportionally, then the ratio is not affected by eta. So there is no eta in there, but there is going to be eta in this side. Okay, and then again minus alpha 1 log of y1 minus alpha 2 log of y2 and so on. Okay, so let me just put plus b in here, and then I will go when you remove this eta from this side, so log of x1 and then minus eta, right? I'm taking it to the other side, so that is going to be again everything else in here, and then again b plus eta. Right? So this is again, they change the sign from v minus u to v plus u, that type of thing, right? So this is again a cost function formulation. So going back to what this data code was saying, that okay, you need to say that what is the orientation? Is it output orientation or input orientation? Now you need to tell SCADA or whatever software you are using, because that will dictate the computer to use the appropriate method. If you say the orientation is output, then it's going to be v minus u. If you say that orientation is input, then it will be using v plus u. Okay. Now here again we are changing notation. Instead of u, we are saying eta. But mathematically, what is happening is plus or minus, right? Plus when you are using a cost function or input distance function, minus when you are using a production function or output distance function. Okay. So again, you don't need to know anything new. So no new estimation technique is needed. Or no new, okay. So you see that while knowing how to run SFA can give you a lot of things. I mean, it's not that you have to learn something new for every model that you are using. Now, I'm not sure whether you are here in the morning session. Again, when he was talking about that, he also introduced stochastic frontier, and he was not talking about production function as such, but when I was talking to him, he said, well, he mentioned some other potential applications, and I'll be also talking about this non-standard application sometimes tomorrow. I mean, one of the sessions. Okay, that means you don't have to always think that, well, okay, all I did in the whole period is talking about production function, and you might be saying that, well, that's not what I want to do. I want to do something else. Okay, so I'll be giving you some examples, and then again I will be saying that, okay, what you want to know in order to use this tool. What type of situation you have to encounter to use this particular tool. Okay, so again, this is we are talking about input and output distance function. What do you want to do? Okay. So then again, this is all done. Now let me talk about translog reduction function, because you are or I've been talking about this Cobb-Douglas. So again, like Cobb-Douglas. What is a Cobb-Douglas? Cobb-Douglas, I told you that this is log linear. So if I write f of x and I just say, well, this is Cobb-Douglas, what it means is that, well, you can write it as a linear function in log. Okay. So this means that if you write y equal to f of x, and if it is Cobb-Douglas, then you can write log of y is equal to, it's a linear function, you know how to write a linear function, right? So this is going to be beta 0 plus sum of beta j log of xj for any number of j 1 through big J. Okay, so this is kind of a linear function in log. Okay, now again, when you do translog, this is another thing that you have not probably seen, but again, this is not something very hard. The translog is a quadratic form in your logs. Okay, so this is linear and this is quadratic. Okay, so I mean, you can just say, well, if it is quadratic, then how do I write it? Well, quadratic means you have the linear, right? So as before, and then you have to add some extra term, right? And what are those extra terms? If it is quadratic, let's think in terms of only 2. So in a if you have 2 x's in log, what are the quadratic terms? I mean, you know the equation of a quadratic function, right? So what do you need for quadratic? You need or polynomial of degree 2. polynomial of order 2. So what are those other? That means you have to think in terms of the term for which the sum of the exponent is equal to 2. So what is the first one? That means you take the square of the first one, so log of x1 square, and then log of x2 square, and then product of x1 and x2, log of x1 times log of x2, right? That will be kind of a quadratic specification of the function. So if you have many, then we just say that, okay, then you can write it out like this, double sum, and like let's say the I and j, and then again I can write beta I and j log of xi times log of xj. Now you can see that, well, if I equal to j, then this is going to be the square, right? And if I not equal to j, let's say I equal to 1, j equal to 2, then you get the cross product, right? So you can get all the cross products like that, okay? So this is how we just write down the translog function. So again, this is not something that is difficult. It is simply looking at a function that's linear versus a function that is quadratic. That is the only difference. Now there are of course certain advantages in having a translog. If it is like this, then what is the elasticity? Right? So this, you see that one, that is exactly the same for all observations, right? If you are looking at the farmers and you say, well, what is the input elasticity? Elasticity of fertilizer, and then say, well, that's going to be the beta F, okay? And this is exactly the same for every farmer. Now we started thinking, is that reasonable? Probably not, right? Or you can just say, well, I mean, I don't want to believe that unless the data tells me that that is indeed the case, right? Okay. So what you want to do is you allow the possibility which is more flexible than again what the Cobb-Douglas says. Right? So now when you get to here, what is the derivative? So that's going to be equal to beta j as before, and again there will be another term coming from here, and that's going to be 2 times summation of beta ij sum over I, and then log of xi. Okay, so you have this extra term in here. Okay, that is going to, and remember you have x in there. So if x are different for different format, then again this is going to be observation specific. Okay, and observation meaning that if observations are farmers, then this is farmer specific. If the observations are again like your different companies, then these are going to be company specific. And again, like given that we are talking about differences in size and all other things, there is no reason to believe that these elasticities are going to be exactly the same for everybody. Right? So that's kind of the reason why we tend to use more flexible function. So we just said about this is more flexible, and then again, what you can do is you can just see that well, this will reduce to a Cobb-Douglas if beta ij is equal to 0 for all I and j, right? So again, there is nothing wrong in assuming something that is more flexible, because you can say that, well, look, if you don't like, I can restrict it and make it Cobb-Douglas, or you can test econometrically, test whether beta ij is equal to 0. So you run a function with Cobb-Douglas, run another function with a translog, and then again see the difference. Test that you can use to find out what is appropriate. And again, like people still do that. I mean, they use Cobb-Douglas for simplicity, but then again, like they say that well, we also use translog, and then again they report results that what would happen if they use translog. Okay, because if you want to publish papers, then using a Cobb-Douglas is most of the time difficult to publish, because people will just immediately ask, why are you using Cobb-Douglas? Okay, so this is again some function which I was thinking from day one that I should at least introduce it to you, just like other things. And again, since this is mathematics, I don't think that you should have any problem in understanding. As I said, that one is linear in log, the other one is quadratic in log. Okay, so that is kind of the only difference. Okay, so that's basically what is going on in here. Now let me see how the setup. So should I continue for 2 hours?
Yes, sir.
Oh, okay, okay.
Sir, you can continue up to 4 p.m. sir. You have one.
Yeah, my
And we have one tea 15-minute tea break, sir. Also at 3:15.
3:15.
Yes, sir.
Yes, sir.
Oh, okay. So I have 15 minutes to continue, right? Okay.
Right, sir.
So the other slides I told you that they are there, and again you have access to those. And if you look at those, I have not 1 or 2 inputs. I have m inputs and then outputs, and then eventually I have the translog functions. So everything is in there, but as I said, I didn't go through those things because of the fact that they are dense. Okay, a lot more dense. The way I did it is just like teaching in a class, right? That is to write everything in front of the participants so they can see. When you have the PowerPoint or this type of thing, you just see the equation and it goes in the next minute, right? Before you feel that, what was there. Right? So it saves time, but again, it's useful only when you know the material more or less, right? But if it is something new, if I'm teaching, I don't do any of those things using this PowerPoint. So I still use the pen and like a paper, meaning that this iPad to derive those things. Okay. Because otherwise, again, nobody will get those things. Okay. So again, as I said, this has everything, but it's quite dense. You can see that this is equations after equation. But I gave you the simple illustration of these concepts using 2 outputs and 2 inputs. Now, what I didn't do it the translog part, but again, like you can also do the translog part quite easily. And again, if you want to do it, again, like this is the translog function that is seen here, and it has multiple inputs, multiple outputs, and a lot of terms. And then again, like I'm imposing the constraint is that means normalization. Remember, I said normalization. Normalization here is going to be a little bit different. But anyway, you get the message. That is main idea of what I wanted to do. Let me see what is in my list here. Okay. So let me just talk about something else. I can create a new page or. Okay, so remember at one point I was talking about again the farmers might face credit constraint. So the question is how do you model if your data, you are seeing the data, but again if you talk to the farmers, they might be saying that okay, we are credit constraint, meaning that we wanted to use more fertilizer, more labor, but we are unable to use it because of the fact that we don't have enough money to buy the inputs. Right? So the question in here is that how do you model credit constraint? And again, this is some people in the developed countries. Again, I don't get into the debate of developing versus developed, but again, if you look at the US or Europe, people do this type of work also. Although we realize that that's not very easy, okay, because hardly. In manufacturing, some cases, firms can face constraint because if the firm is not reliable, and again, like you are starting a new venture, and you go to the bank and ask for, you know, like 1 crore, and then very few banks would be willing to pay you that much of money because you don't have the credit worthiness. So the question is, in general, that if you face credit constraint, okay, how are you going to be modeling that aspect of it? Because if you estimate a production function as it is, then again, you are not including the credit constraint. So the credit constraint, the way we'll be modeling it like this. That's what you have this much of money. Okay, so this is the available cash. Okay, and again, like the cost of input is Wx or W prime x. Okay. So credit constraint means that you cannot use inputs that would cost you more than the amount of cash that you have in hand, right? So your W prime x, okay, has to be what? Less than or equal to the cash that you have, right? So when you are talking about, again, like using your inputs, okay, you have to use them in a way that this inequality is satisfied, right? Or if you just, well, not inequality, but you can make it also equal, right? So what is happening is you think in terms of, again, a producer who is maximizing output, okay, and again, they're subject to this constraint, okay. So we are writing again, going back to single output production function, y equal to f of x, and you can put z if you want to, okay. So this is the standard production function, okay. X is a variable input and z are some other you know, environmental inputs, right? Okay. Your objective is to choose your variable inputs. In such a way that you're maximizing your output, and then the constraint is satisfied. So again, we define the Lagrangian, okay, which is going to be your you are minimizing. So let's just do it in two ways: minimizing cost, maximizing output. Instead of doing that, you are minimizing cost, subject to this constraint, okay. So what is happening, the Lagrangian, you can write Wx or W prime x plus lambda, Lagrange multiplier, and then you just write y minus f of x. This is the production function, and this is the, no, you have to do, sorry, keep on, because you have to get this c minus W prime x or W prime x times c. So I get back to the original one, this f of x. Okay. Okay, so let's get to maximize y subject to this credit constant. So what are the first order conditions? Remember, first order condition is taking a derivative with respect to x's. Your choice variables are x's, right? So what you do is you take a derivative of this, okay. So FOC, the first order condition, is fj x minus wj times lambda. So what is fj? That means del f del fj, partial derivative of f with respect to xj, okay. So these are the first order condition for each input. Again, as before, lambdas are there, and again, you are not interested in lambda, these are nuisance parameters, right? So lambdas are Lagrange multiplier, so you want to get rid of them by taking the ratio. So your fj over f1, fjx, f1x, okay, this is equal to wj over w1, okay. So again, like you are getting j equal to 2 through big J. So you are getting j minus 1 equations in the first order condition, and one equation coming from the the constraint function, C minus W prime x. So you solve for x's from this first order conditions along with this C is equal to W prime x. Okay. So if you do that, then what the solution will look like? The solution will be in terms of everything else. And what are those everything else? Other than x, I mean if you look at the setup, other than x, the only variables are y and input prices, right? So this is going to be a function of, let me just put it like this, function of y and then w, and then if you have z, then you just put z. Okay, so this is going to be the, what we call the input demand function. And then you plug this input demand function into the production function. So you have y equal to f of x, right? And you are replacing x by these guys, right? So each of these x is a function of this. So in general, you can just say, well, that is going to be some function, right? So some function of y, w, and z, right? Because each of these x's are function of those variables. So again, like taking all of them together, meaning that, well, that's going to be a function of the same variable, right? So this is called indirect production function. So remember, production function is a function of input quantities, but input quantities on the right hand side are eliminated because we are talking about choosing your inputs in a way that will maximize your output. Right? Okay. So then again, what you do is you think in terms of assuming a functional form, okay, and then estimate it. Now let me just show it and show you in terms of a graph in 2 minutes or 3 minutes what is happening in here. Okay. So let's just say that, okay, this is a production function, okay, and this is y and x, again 1x, and your objective is to maximize output. So what you are doing is you are getting a point of tangency. Well, that's not a very good graph. I mean, anyway, you get the point. So this is the optimal point. So again, you should be using this much of x. So let's call it x star. Okay. But if this x star, so w times x star, if this is bigger than c, then you cannot use it, right? Because it's costing you more than the amount of cash that you have at hand. So what you need to do is you are forced to use a lower level of x. Okay. For example, this much. Okay. So that means, what does that mean? Okay. So this much, meaning that, well, your produced output is going to be less than what the maximum output is going to be. Okay. So again, like relieving the credit constraint, meaning that, well, you will be moving from this point to that point. You will be using more inputs and you will be producing more output. Right? So then again, the advantage of this approach is to know that, okay, so if you know that some formulas are credit constraint, what is going to be the advantage of relaxing the credit constraint? So then again, you can think in terms of what is the derivative of y with respect to c. Okay, so remember, in the indirect production function you have that, so you want to know this. Okay, or if you have logarithmic form, then you want to know this. That means if the credit constant is erased by 1%, okay, by how much your output is going to be in percent. Okay, if it is log, then everything is in percent. If it is not in log, then you just say, well, if you are credit constraint and you are given 1,000 rupees more, by how much your output is going to be increased. So then again, like you can either do this or that depending on what type of function you are using. So then if somebody says, okay, you come up with a setup, what is the use of this? Right? What benefit do I get by estimating this function? Okay, the benefit that you get by estimating is that this, you can think in terms of a policy, okay, or you can tell the government that look, these formulas are credit constraint. If you erase the credit constraint, If you give them easy loan, then again the output is going to go up by this much, okay? Or percentage change in output is going to be this much, okay? So that is one kind of one thing that comes out from this exercise. And then again, I'll stop in here, but again you can add in efficiency in the framework. So for that, you go back in here and then you just add in efficiency in this framework by writing e to the power minus u. So I just change the color to indicate that I'm adding these things later. And you go through the same exercise, nothing will happen in here. So in the end, when you look at the indirect production function in here, there will be again e to the power minus u, or when you take a log, it's going to be like a minus u, so it's going to be v minus u. The same story again. For estimation, you don't need to know anything else. The one tool is going to be enough. Either you use as a cross if you have a cross section data, or you just use as a panel that he's going to be talking about at the end of the session. So again, you don't have to know a whole lot of things. Okay, I mean, if you want to do applied work, I mean, knowing basics of SFA will take you a long way. Right? So all you need to do is come up with interesting ideas, interesting data, interesting issues. Right? Okay, so let me just stop it here. Okay, instead of 15, I did it in 17. So I am going to be talking about two additional things that were not in the agenda, or at least I was not thinking in terms of presenting those things. But again, these ideas might be useful for future. So again, at some point you have to do some research work, right? So you might find these ideas useful at some point in time in the future. So one such thing is what we call good and bad output. Okay, so I'll just go over these things and what we mean by that. Nowadays with pollution, okay, these issues are becoming more and more important. So you think in terms of production of anything, okay, so good meaning that's something that you you want to produce what we call desirable output. Okay. So think in terms of producing electricity. Okay. So that's kind of the desirable output, and you can think in terms of production function or electricity output. Output is electricity, and you have the input side. So you can think in terms of Y, electricity output, and again you have a production function, and you can have your inputs x1, x2, x3, and so on. Okay. Now, when we do this type of thing, we do not consider the side effects of any of this production, right? But no matter what production processes you can think of, everything has some other consequences unintended. So let me just write that. Either you can say the unintended consequences or unintended output. And we call these things as bad output. So what are those things? I mean, producing electricity, meaning that, well, you are burning coal or a gas, and again there is some emission, right? So again, that's basically your bad output. You do not want to produce that. But the technology is such that, well, you cannot burn coal and not generate pollution, right? So again, like in agriculture, they are also again doing something that they are using chemical fertilizer, and that's contaminating the water supply, right? So the residuals go to the water system. Okay, so you can think of anything, any production process. Okay, you will have this type of things. Okay. So what we want to do is, again, you can say that, well, look, in the production function, we do not take into account those type of activities. but in principle one should do that, because if you are thinking in terms of green productivity or those type of things. What is green productivity? I mean, you just talk about the regular usual productivity, and then you can factor out this side effects or negative consequences. Okay. So one other way of explaining this thing is this way. That means you have externality. Okay, so again, externality can be externality in consumption or production, but here we are talking about production. So you are producing something, okay, but it's causing some other, outputs, and that is negative, okay. That means the pollution is not positive, right? It is affecting human health or many other things, right? I mean, global warming in general, but again, if you don't want to go that far, at least you know that it's affecting human health, right? And again, people living in Delhi, I mean, now Delhi is one of the world's most polluted city, okay? Some years ago, we would be thinking that's Mexico City, but now Delhi is basically surpassing all the cities in the world, okay? So you know that, well, that is going to be affecting human health, okay? So what happens when this air quality index goes in I don't know what is the, I just told you that, well, that Delhi reaches the maximum or is beyond the maximum, okay? So, the schools are closed on those days when it is really bad, and you can stay inside. Well, that will be mitigating some of the effects, but you have to come out, right? So the question is that, well, I was looking at AQI or air quality index, and I just said, well, I thought that this place is going to be a lot better than the other. I think it's still better because I'm not looking at AQI for Delhi, but again, I have Kolkata in my phone, so I'm just looking at both, and I just see that, well, this Rohtak and Kolkata has similar AQI. So since we always go to Kolkata, not Delhi, we'll be thinking that, well, Kolkata weather is better than Delhi, but not necessarily. Kolkata is also not very far behind. I mean, it's catching up. I mean, in bad way, right? So the question is, again, without going into those details, we know that it has consequences. So one thing that I talk to my students is, well, if you can get data on this type of thing, that means, we're talking about pollution, and we want to know the effect of, we want to study the effect of those things on human health. So the question is, again, when you have AQI very high, what type of disease or what type of problems people will have, okay? So you can get those information from, people go to hospital, so let's think in terms of not staying at home and getting cured, but case situation is bad and you have to go to the hospital. So there is a record. But the problem is that, well, those type of information is not that easy to get, okay? You cannot approach to the hospital and say that, well, I want to know those things. There are all sorts of rules and regulations, okay? But the point is that, well, we know that there are consequences, and that, most of the time people say that, well, your lifespan is going to be reduced by 10 to 15 years if you live in this type of situation. We talk about smoking, and we just said, well, if you stay in Delhi for 1 month, and every day it would be more than smoking 1 pack of cigarettes, right? So cigarette smoking is bad for health, we just talk about it, but nobody talks about living in New Delhi is bad for your health. Now we cannot talk about that because you said, well, what do I do? Smoking you can quit, but you cannot quit, so that, well, I'll go somewhere else. So the idea is, again, we know that these are serious issues, right? But again, most of the time when you estimate a production function, we ignore those things. So what happens is, again, there are 2 reasons. One is that, well, we want to look at the effect of those things on productivity or TFP. It can be, TFP can be very high by burning coal that is very bad quality coal, okay? So the question is that, well, if you factor out those, your TFP might be very small or even negative, right? So you should not be thinking that well my TFP growth is very high. Now in China that was happening, but Chinese government realized in a hard way that again this is not working. So the last few years they are making all sorts of efforts to mitigate pollution. Most of the manufacturing plants or activities they took it out from the city to the suburb. Okay, because again I think it's probably the same in New Delhi, but one time I was in Beijing and I was asking that, well, do you see the sun? They said, well, not really. I mean, you can see the sun occasionally because the sky is never clear. Okay, so that's one thing that they did, that they removed or moved all the manufacturing facilities outside the city. And then the other thing they did is just they plant many trees. So again, in a gap of 10 or 15 years, I went to, first time I was in Beijing, and the second time when I went in there, I just said that, oh my God, this is completely different. So they have trees everywhere, okay? So going from Beijing to another city where there's a conference, and again, you could see the highway, but nothing beyond the highway. Everything is covered with trees, okay? So again, these are some of the steps, but again, in China, they can do certain things, but in other countries, because of the democratic setup, they cannot do those things that easily. In China, they want to do it, okay, they will do it because they don't need to worry about the other things. There is a busti or something like that, they will get rid of that overnight, right? But in India or some other countries, you cannot do that, okay? So the question is, again, we want to bring that into the picture. So if you just say, well, this bad B is the bad output, then bad output will depend on what? Okay, bad output will depend on, so think of bad output as pollution, or again, release of SO2 or CO2 in the air, okay? So that will depend on how much good output you are producing, how much electricity you are producing. If you stop producing electricity, there will be no CO2 coming out of that, right? So it's directly related to how much good output you are using. And then the other thing you might just say, well, okay, there are some X variables. Let me just use different notation. These are the inputs that will go into the production of bad. What do you mean by production of bad? Then we should think of opposite of mitigation of bad. So again, you can take steps to mitigate release of SO2 or CO2 in the air. Right? And again, there are different devices you can install some of those devices so that the release is going to be less. It's not going to be zero, but you can minimize that. So same thing is for the car. In the exhaust pipe, they have kind of certain devices that you have to install. But again, people often cheat. I mean, I remember first time, because in the US, I went to California to do my PhD, and California is one of the states where they're very strict on this type of thing. So people will take their car to DMV, this motor vehicle department, to test, right? And then again, before you go to this is like in India or some other countries. So there are some places where you can fix those things, right? So set it up and then go for testing. So you pass because you have installed that device in your exhaust system. And as soon as you come out, you just take it out, right? Because that will even, so what is the consequence of doing it? Because it will reduce the speed, and it will also reduce the gas mileage, okay? So you don't want to, from your point of view, if you're ignoring all the environmental consequences, you don't do that. So nowadays they have a thing that in order to sell a car in California, you have to have those things installed permanently. You cannot sell a car in California without those things. Okay, for California it's different from other states. Okay, because so you can impose some of those restrictions. So anyway, so B, again thinking in terms of only one B, you can have many of those things. Right? So you can just write it out like this. So what is happening is that you can think of estimating this as it is because it is not affecting B. So if you look at the relationship, okay, so you have Y and Y is generating B, right? and again like, but B is not affecting your Y directly. Okay, so to say that okay, the CO2 or SO2 is affecting production of good output, what would be the intuition? That means your bad output is so bad, that means the pollution is so bad, that means it is affecting your health and you are becoming less productive. So we have not reached that stage. So that's why we just say that, well, it goes like this. So Y affects B is going like this, but B is not affecting Y. Okay. So again, if you look at these two equations, Y is not, there is no B in the first equation. Because to put B in the first equation, you will be interpreting that B affects production of good output. No, production of B, a bad output, is determined by how much good output you are producing. Right? So this is the setup. So again, like this is a simultaneous equation or two equation. The first equation you can estimate as it is, as we were talking about, and again, like use this Y that you are getting from the first equation in the second equation, and estimate this bad output equation. So the question is that, well, why do we talk about bad output? I mean, what is the benefit of using it from a practical point of view or from doing the study? Okay, so what we do is that, well, we are interested in, or government is interested in what is called the shadow price of B. Okay, what is that? Now, if you sell something in the market, let's say well, you are growing vegetables, you are selling in the market, so we know what the price is, right? Because it's marketable, right? But even SO2 or CO2, is that product marketable? No. Okay, but again, you can think in terms of negative price, but again, like you don't buy SO2 or CO2. What happens, the government sometimes permits some, issues some permits that you are allowed to pollute this much. And then again, that amount you can sell it to another company. So that, well, the total is exactly the same, but you are allowed to sell. Sometimes you are allowed, sometimes you are not allowed. But the point is that, well, it is not, again, this type of products, if you call them products, they are not marketed. That means there is no price that you can observe. So that's why we use the word shadow price. So we are interested in calculating what is called the shadow price of it. So the reason for calculating shadow price is that we want to tax, let's say, well, the companies that are polluting or the plants that are polluting the air. Okay. So the question is, what would be the basis of the tax? Okay. If you know the price of it, then you can just say that, okay, you pay a price for polluting the air, because this is the price of the CO2, 1 ton of CO2 or SO2. But again, there is no market. So what we are interested in is getting this, what we call the shadow price. So we are interested in getting this. Okay. Now, since you cannot reduce B without reducing Y, the question is how much good output you have to give up, okay, to reduce your pollution by 1 ton. Okay. So that is indirectly the shadow price. Right? So to reduce your pollution or CO2 by, let's say, 1 ton, you have to give up the production of electricity by a certain amount, and again, like you know the price of electricity, so you can think of what is the revenue loss. Okay, what sort of revenue you will be losing when you plan to reduce your production of B. So this question is that, well, we are interested in finding out this. This is going to be treated as the shadow price, because if you want to reduce B, you have to reduce your Y. So this is going to be a positive number, and that can be interpreted as the shadow price. Okay. And then the model that we use is basically this. So from here you can get dB, dy, and if you use the assumption of monotonicity, then again you can take the inverse of that to get dy dB. Okay. So again, this type of models are quite popular. Recently I wrote a paper with a PhD student. Again, in that application we use banks. Bank is not the best example, but in that example we are talking about banks are producing some outputs. These are different type of services, and then the bad output is, well, this is the bad loans that they have, the loans that they are are not able to recover. So we treated that as loan loss or bad loan is what we treated as bad output. So then we have a setup like this, and we use, I think in that paper we use ES data to estimate again the shadow price of this bad loans. Okay. So this is becoming a major problem in India, especially because of the fact that banks are nationalized, so nobody is directly responsible for that, or at least they say that okay, in the end government is going to be taking over or paying for our losses and things like that. So remember I mentioned that bank denationalization, whether this was based on an efficiency ground, and again when we talk about efficiency, we are also talking about efficiencies related to the bad loan. So this is also something that you can do either directly using a single equation, production function or a cost function, or you can go through this type of exercise. Okay, that means you do a setup that the production of loans and other things are the usual production function using capital, labor, and that type of thing, and then the loan, bad loan, depends on again the amount of other activities that you are doing, and of course we also know, but again there is no data that who is doing how much of what do you call it, when you give a loan, whether you are looking at the credit worthiness of the person taking the loan, how careful you are. Otherwise you won't have what is this guy's Nirav Modi or that type of person. I mean, when I heard the news, I said, well, how can one person get that much of loan, right? Without anybody checking, or everybody is checking, but so everybody has to sign. Now, you know that I worked in a bank for 6 months. So here, the way the system goes, that there will be a series of signatures, right? So everybody signed, and knowing that well, this is a fraud type situation. And then again, this guy is now again government. I don't know whether our prime minister is kind of giving him some leeway or something like that. But he is in UK, right, in London, with several flats that he owns. He has his own life at the expense of the Indian taxpayers. So again, like if you have data on those type of things, that means how corrupt a particular bank is, then again that should be included in the analysis. So that would be, in my mind, that would be something very, very interesting. But the question is, you have to investigate how to get data on corruption level of not each and every officers in the bank, but again at the bank level, whether you can relate it to that specific corruption level. So that would be something really nice. Okay, so I just gave you kind of a flavor of this type of thing, and then the rest of it is you just do TFP, and then you factor out the contribution of the bad output, because again you need to take it out because that's bad from the societal point of view. For an individual point of view, you care about TFP, but for the society's point of view, it says TFP minus the contribution of this bad output. Okay? Okay, so I think my time is up. So now you'll be learning some SCADA for panel modeling and stuff like that.
Thank you, sir, for your valuable insights.